July 10, 1940, and the Royal Air Force has a problem that's killing pilots faster than German bullets. Above the English Channel, squadron leader James "Ginger" Lacey pushes his Spitfire into a desperate dive to escape a Messerschmitt Bf-109. The moment his stick goes forward, the Rolls-Royce Merlin engine coughs, sputters, and dies. For 3 eternal seconds, Lacey's aircraft becomes a glider at 15,000 feet while the German fighter closes in, its MG-17 machine guns already flashing. The engine roars back to life when he levels out, but it's too late. Bullets perforate his fuselage, shredding aluminum like paper. Lacey survives by pure luck, nursing his damaged Spitfire back to Biggin Hill. He's the 3rd pilot this week to report the same impossible problem. Spitfires, Britain's most advanced fighters, are dying in the air not from enemy fire, but from a design flaw nobody saw coming. The aircraft that's supposed to save Britain can't perform the one maneuver pilots need most to survive: the -G dive. In aerial combat, those 3 seconds of engine failure are a death sentence. Fighter command is losing an average of 8 Spitfires a day. At this rate, they'll have no operational fighters left by September. The Germans have noticed. Luftwaffe intelligence reports are calling it the British weakness and training their pilots to exploit it. The Battle of Britain hasn't even officially begun, and the RAF is already losing. Before I tell you how a female engineer with a motorcycle obsession solved this crisis with nothing more than a brass washer and a drill, let me ask you something. Ever wonder why the most sophisticated military minds sometimes miss the simplest solutions? Comment below where you're watching from and hit subscribe, because you won't believe how a 2-shilling part ended up saving Western civilization. The numbers are staggering. Between May and July 1940, 43% of Spitfire combat losses involve engine failure during evasive maneuvers. Not enemy fire, not pilot error, engine failure. Spring 1940, and Britain's entire air defense rests on 2 aircraft, the Hawker Hurricane and the Supermarine Spitfire. The Hurricane is reliable but slow, topping out at 340 miles per hour. The Spitfire is the thoroughbred, capable of 370 miles per hour in level flight with its Rolls-Royce Merlin 3 engine producing 1,030 horsepower. On paper, it matches the Messerschmitt Bf-109E, Germany's premier fighter. On paper. The Merlin engine uses an SU carburetor with a float chamber system, standard technology since the 1920s. In normal flight, gravity keeps fuel in the bottom of the chamber, where the float valve regulates flow to maintain a constant level. It's simple, reliable, and works perfectly as long as the aircraft maintains positive G-forces. The manual states clearly, engine performs optimally at all normal flight attitudes. The key word nobody questioned was normal. You're sitting in a Spitfire cockpit in June 1940. The canopy gives you excellent visibility. Your right hand grips the control stick, left hand on the throttle. The Merlin engine thrums smoothly at 2,850 RPM. Everything works exactly as Supermarine's engineers intended. Then a 109 appears above you, diving at 400 miles per hour. Your training says push the stick forward, dive away, use your superior turning ability at high speed. You push forward. Instantly, you're thrown against your harness. Dust and debris float up from the cockpit floor. Your stomach rises into your chest. This is -G, and your carburetor float is now pressed against the top of its chamber. Fuel either floods uncontrolled into the engine, causing it to choke, or the flow cuts entirely. Either way, your engine dies. The German pilots don't have this problem. Their Daimler-Benz DB601 engines use direct fuel injection, a Bosch system that forces fuel directly into cylinders regardless of gravity. A Bf-109 can fly inverted, pull -G, perform any maneuver its airframe can handle. The engine never misses a beat. German pilots call it following through when they push their fighters into pursuit dives. British pilots call it the death push. By July 1940, RAF pilots have developed workarounds. The half-roll maneuver, Roll inverted first, then pull back on the stick to maintain positive G throughout the dive. It works, but costs 2 to 3 crucial seconds. In combat, where positioning determines survival, those seconds mean death. Flight Lieutenant Alan Deere reports, "The Huns know our weakness. They climb above us and dare us to follow. If we push over, we're dead. If we half-roll, they're gone." The statistics from France are damning. During the Battle of France in May 1940, the Armée de l'Air lost 250 fighters in 2 weeks. RAF squadrons sent to help lost 386 Hurricanes and 67 Spitfires. Post-action analysis shows that in 31% of Spitfire losses, pilots reported engine failure during combat before being shot down.
Le défaut anglais, the English defect. Squadron leader John Ellis describes a typical engagement. You spot them coming in from the sun, 12 Heinkels protected by 20 F-139s. You climb to engage. Les F-139s roll over and dive through your formation. You can't follow. You have to let them go, circle back, hope they haven't reformed below you. Meanwhile, the bombers drone on toward London. Le Luftwaffe notices immediately. A captured German intelligence report from June 28, 1940 states, British Spitfire Type 1 and Type 2 exhibit consistent engine failure in negative gravity maneuvers. Recommend all units exploit this weakness through high-angle diving attacks. The Germans are literally writing tactics around British engine failure. Rolls-Royce engineers insist the solution is complete engine redesign. They're developing the Merlin Fant X with improved supercharging, but it still uses a float carburetor. A proper fuel injection system would take 18 months minimum to design, test and deploy. Britain might not survive 18 weeks. Lord Beaverbrook, Minister of Aircraft Production, holds daily crisis meetings. The wastage rate is unsustainable. They're producing 560 Spitfires par mois, but losing 400 à toute cause. If engine failures could be eliminated, operational strength would increase by nearly 30%. The mathematics of survival are that simple and that brutal. By early juillet 1940, 11 différentes solutions sont under consideration. Bendix-Stromberg pressure carburetor from America. Modified French injection system. Even a gravity-independent carburetor design using mercury switches. All are complex. All require extensive testing. All will take months Britain doesn't have. What nobody at ces high-level meetings knows is que 170 000 à Nord, à la Royal Aircraft Establishment in Farnborough, a young femme est en train de solver leurs problèmes avec une solution si simple que seniors ingénieurs vont initialement refuser de croire que ça marche. Beatrice Shilling et 31 ans en 1940, une de seules 3 femmes en Bretagne avec un diplôme en mécanique ingénieur. Shilling a eu sa BSc de Manchester University en 1932, où elle était la seule femme dans sa classe de 87 étudiants. Sa thèse était sur le superchargeur design pour racing engines. Son professeur Colette remarquablement intuitif pour solutions inconventionnelles. Shilling ne look pas comme Central Castings idée de l'ingénieur. Elle est 5'4", porte rond de spectacle et reste motocyclette sur le week-end. Shilling a une Norton 500cc qu'elle a modifiée elle-même, augmentant sa top speed de 95 à 106 000 à l'heure. À Brooklands Racing Circuit, chez Nunn pour prendre les bancades avec des angles qui font saisonner les riders. Son racing name est Tilly the Terror. She joined the Royal Aircraft Establishment en 1936 comme un technical officer, officiellement un assistant à senior ingénieur. Unofficiellement, c'est la personne qu'il cale quand quelque chose ne marche pas et Naveltel n'ose pourquoi. Elle a une réputation pour voir pattern autre miss. Quand un nouveau Hurricane prototype souffrit mystérieuse vibration, Shilling identifia résonance entre la propeller et telle surface en 12 minutes. Et avait stampé un team pour 3 semaines. Son workspace est chaos organisé. Carburetor parts couvre un bench, motorcycle components occupy another. Technical manuals en anglais, german et français sont stacked partout. Shilling lit german technical journals, incluant ceux sur Bosch Fuel Injection Systems. En lait qu'à ses collègues, elle sait exactement comment les ennemis ingènes work. En août 20 1940, Shilling rit le combat report de Squadron Leader Lacey's Near Fatal Engagement. Something clicks. She's seen this problem before, not en aéroplan, mais en motocyclette racing. Quand un Norton touche sévère bumps à speed, le carburateur float bounce, causant momentané fuel starvation. La solution sur sa bike was simple, restreindre maximum fuel flow pour que l'engine can't float, mais maintenir assez de flow pour full power. Ce soir-là, elle sketch un dessin sur le bas d'une enveloppe. Un brasse-disque avec un précisément calibré trou installé dans la fuel mine juste avant le carburateur. Simple à manufacturer en heure, cher à masse-produire, aisé à installer pour squadron mécanique. Le trou est critique, trop large et flaving continu, trop petit et combat power est réduit. Elle passe toute la nuit à calculer. Le Merlin 3 requiert 42 gallons par heure à combat power. En négatif G, fuel pressure increases by a factor de 2,3. Donc, le restricteur trou doit être exactement 0,292 inch en diamètre. Elle triple-check les mathématiques. À 3 heures du matin, elle machine un prototype dans le workshop utilisant un brasse blanc et un précision drill. Le lendemain matin, elle présente sa solution à Wing Commander Harold Stevens, son superviseur. His response est incrédule. Vous proposez de régler notre merclus critique en battage avec une washer. Shilling's réponse est caractéristiquement directe. It's not a washer, it's a calibrated orifice restrictor, and yes, it will work. Stevens examine ses calculs. La théorie est sound, mais la solution semble insultantement simple. La RAF est entendue complex engineering.
Shilling is offering a brass disc with a hole in it. He forwards her proposal with the lukewarm endorsement. Miss Shilling's suggestion merits investigation, though I have reservations about such a rudimentary approach. The proposal reaches the Air Ministry on August 24, 1940. The initial reaction is dismissive. Air Commodore John Slessor writes in the margin, "Are we really considering this workshop fix for our premier fighter?" Someone else adds, "Miss Shilling's Orifice," a term dripping with condescension that will stick throughout the war. Rolls-Royce engineers are openly hostile. Sir Stanley Hooker, chief engineer, states in a meeting, "This is precisely the sort of ham-fisted solution I'd expect from someone who tinkers with motorcycles. The Merlin requires proper fuel injection, not plumbing modifications." He predicts the restrictor will reduce engine power by at least 15%, making the Spitfire unable to catch German bombers. The bureaucratic resistance is enormous. Form 124B must be filed for any fighter modification. Technical committee approval requires unanimous consent from 12 members. The Modification Review Board meets monthly. Following normal procedures, Shilling's restrictor wouldn't be tested until November at the earliest. But the Battle of Britain is intensifying. August 24, the Luftwaffe accidentally bombs London. Churchill orders retaliation against Berlin. The air war escalates beyond anything previously imagined. The RAF is flying 700 sorties daily. Every Spitfire matters. Every engine failure could mean a sector station overrun. Flight Lieutenant Jeffrey Quill, Supermarine's chief test pilot and Spitfire expert, reviews Shilling's proposal. Unlike the bureaucrats, he immediately grasps its elegance. "It's so simple, it's brilliant," he tells Air Marshal Hugh Dowding. "We should have thought of this months ago." On September 10, 1940, with German invasion barges massing in French ports, Dowding makes an executive decision. Bypass the committees. Test it now. He personally calls Shilling. "Miss Shilling, how quickly can you produce 20 restrictors?" Her answer, "They'll be ready in 6 hours, sir." She works through the night with 2 assistants, machining 20 brass discs to exact specifications. Each is stamped with a serial number and tested for flow rate. At dawn on September 11, she personally drives them to RAF Duxford in her Morris 8, arriving as the morning patrol is landing. The pilots chosen for testing include Squadron Leader Douglas Bader, the legendary legless ace who commands 242 Squadron. Bader is skeptical of gadgets and particularly dismissive of solutions from boffins.
When told a female engineer has developed a fix for the negative G problem, his response is unprintable, but essentially translates to disbelief. September 22, 1940, 7:45 a.m. Tilly Shilling personally supervises installation of restrictor serial number 001 in Bader's Spitfire X4590. The procedure takes 45 minutes. Remove the fuel line connection, insert the brass disc, ensure proper seating, reconnect. No special tools required. Any competent mechanic can do it. The first test flight is scheduled for 8:30 a.m. Bader takes off with 3 other modified Spitfires. They climb to 15,000 feet over Cambridgeshire. The test protocol is simple. Progressive negative G pushes from -0.5 to -2.0, holding each for 5 seconds. Monitor engine response. At -0.5 G, slight engine roughness but no failure. At -1 G, the engine coughs once but maintains power. At -1.5 G, definite stuttering but still running. At -2.0, the engine maintains 85% power for 8 full seconds before Bader has to level out. Without the restrictor, the engine would have died completely at -0.5 G. Bader's voice crackles over the radio. It works! The bloody thing actually works! He performs 3 consecutive negative G dives from 20,000 feet. Each time, the engine maintains sufficient power for combat maneuvering. After landing, his assessment is brief. Install it in every kite we have, tomorrow. But the real test comes 2 days later. September 24, 1940. 11 p.m. Bader leads 12 Spitfires from 242 Squadron on patrol over the Thames estuary. All have been modified with Shilling restrictors. They encounter a formation of 30 Dornier D-17 bombers escorted by 50 Bf-109s at 23,000 feet. The 109s are high, expecting the British to climb gradually to engage. Instead, Bader orders an immediate zoom climb followed by a diving attack through the German formation. It's a maneuver that would have been suicidal 3 weeks earlier. His Spitfire pulls negative G at the top of the climb, pushing over into a diving attack. The engine coughs but doesn't quit. Bader fires a 3-second burst into a 109 from directly above, a position he could never have achieved before. The German fighter, not expecting attack from that angle, explodes. Bader continues through the formation, maintaining power throughout the negative G dive. The entire engagement lasts 12 minutes. 12 modified Spitfires claim 8 confirmed kills with 2 probables. More importantly, they suffer no losses. For the first time since May,
a Spitfire squadron has engaged superior numbers without a single engine failure. Flight Sergeant George Unwin, flying as Bader's wingman, describes the transformation. It was like someone had unchained us. We could finally fight the way the aircraft was meant to fight. Push over, follow through, maintain pursuit. The Jerrys didn't know what hit them. September 27, 1940 becomes the proof of concept. The biggest daylight raid yet. 80 Heinkel HE-111 bombers escorted by 120 Bf-109s heading for London. 12 Spitfires from 603 Squadron, all modified with restrictors, intercept over Kent. Flight Lieutenant Sheep Gilroy executes what becomes known as the Farnborough dive, a pure negative G bunt that puts him directly on a 109's tail. The German pilot, Oberleutnant Franz von Vera, can't believe a Spitfire has followed his evasion. Gilroy shoots him down in 3 bursts. Von Vera survives, but is captured. During interrogation, he insists, "Your pilot did something impossible. Spitfires cannot do such maneuvers." The modified Spitfires of 603 Squadron destroy 17 German aircraft while losing only 2 of their own, both to overwhelming numbers rather than mechanical failure. The restrictor has transformed the Spitfire from hunted to hunter. Word spreads through fighter command like wildfire. Shilling's Orifice works. Pilot Officer Eric Locke, who scores 3 victories that day, writes in his combat report, "Engine maintained power throughout negative G maneuver. Pursued 109 through vertical dive from 25,000 to 8,000 feet. No engine failure. Destroyed enemy aircraft at 7,500 feet. This modification has saved my life and will save many others. The psychological impact is immediate. RAF pilots who had been flying defensively, afraid to pursue, suddenly regain confidence. Squadron leader Brian Lane of 19 Squadron reports, "The boys are actually looking forward to engagements now. They know they can follow the Huns wherever they go." German signals intelligence intercepts RAF radio traffic during the September 27 battle. Luftwaffe headquarters in Paris receives urgent reports. British fighters exhibiting new capabilities, maintaining pursuit through negative gravity maneuvers. Request immediate tactical review. The Luftwaffe's initial assessment is that Britain has somehow developed and deployed fuel injection in record time. General Adolf Galland, Germany's fighter commander, writes in his diary, "The Spitfires have changed overnight. They dive like our Emils now. What have the British done?" A crashed Spitfire is recovered near Calais on October 2. German technicians dismantle the engine, expecting to find a complex injection system. Instead, they discover Shilling's brass restrictor. The report to Berlin is incredulous. British modification consists of simple brass flow restrictor, designation unclear, diameter 7.4 millimeters, no moving parts, cost estimate 2 Reichsmarks. Reichsmarshal Hermann Göring refuses to believe it. A brass disc? Impossible! There must be additional modifications we haven't found. He orders further analysis. 3 more captured Spitfires reveal the same simple restrictor. German engineers are astounded that such a basic solution has neutralized their tactical advantage. The psychological impact on German pilots is significant. Hauptmann Helmut Wick reports, "We can no longer simply dive away when threatened. The Tommies follow us down. We must fight on equal terms now." The Luftwaffe begins calling modified Spitfires Tauchspitfire, diving Spitfires. German tactics change immediately. The high-altitude diving attack, their standard opening move, becomes less effective. They're forced into turning battles, where the Spitfire's superior maneuverability gives it advantage. Loss rates for Bf-109s increase by 30% in October 1940 compared to August. Intelligence officer Major Joseph Schmid writes, "The British have negated our technical advantage with a modification so simple our engineers are embarrassed they didn't anticipate it. We must assume all Spitfires now have this capability and adjust tactics accordingly." The Germans attempt countermeasures. They develop new combat formations, emphasizing horizontal attacks over vertical. They increase bomber escort ratios. They schedule more raids at dusk when lengthy pursuits are impossible. But the fundamental equation has changed. The Spitfire is no longer vulnerable. Fighter pilots develop new nicknames for the restrictor. British pilots call it Tilly's Orifice with newfound respect. German pilots refer to it as Der Englischer Trick, the English trick. One captured German pilot admits, "We thought you had copied our injection system. When we learned it was just a disc with a hole, our engineers couldn't believe it." The restrictor's effectiveness forces the Luftwaffe to abandon its plan for achieving air superiority through fighter sweeps. They can no longer rely on technical advantage to overcome British numbers. The Battle of Britain becomes a war of attrition Germany cannot win. Production begins immediately. Shilling trains teams of technicians to manufacture restrictors. The specifications are exact. Brass stock 1.5 millimeters thick, hole diameter 7.42 millimeters plus or minus 0.5 millimeters, edges deburred to prevent fuel cavitation. A competent machinist can produce 20 per hour. By October 1940, mobile installation units are visiting every fighter command station.
3 technicians can modify 8 Spitfires per day. Priority goes to 11 group squadrons defending London, then 10 group covering the southwest, then 12 group in the Midlands. By November 1, 1,847 Spitfires have been modified. Shilling personally oversees quality control.
Each restrictor is tested for flow rate before installation. Serial numbers track every unit. If an engine shows any performance degradation, the restrictor can be traced back to its manufacture date and technician. The defect rate is less than 0.3%. Training for squadron mechanics takes 2 hours. Remove fuel line, insert restrictor with arrow pointing toward carburetor, retighten connection, test engine at full throttle. Check for leaks. Pilots receive a simple briefing. You can now pursue through -G. Engine will maintain 85% power for up to 10 seconds. Don't exceed -2G for more than 5 seconds. The Mark II restrictor, developed in December 1940, features a variable orifice adjusted by altitude. At 30,000 feet, where fuel pressure is lower, the hole automatically enlarges by 0.3 millimeters. This maintains consistent performance throughout the Spitfire's operational ceiling. Installation procedure remains identical. Spitfire production incorporates the restrictor as standard equipment from January 1941. The Mark V Spitfire, entering service in February 1941, features an improved restrictor design with a secondary anti-surge valve. Performance in -G improves to 92% power retention. Field modifications continue. Pilot Officer James Johnson develops a technique for cleaning restrictors without removal, using high-pressure fuel flow during ground runs. This reduces maintenance time by 75%. His procedure becomes standard throughout Fighter Command. By March 1941, 3,000 Spitfires have been modified. Production reaches 200 restrictors daily across 4 facilities. Cost per unit, 2 shillings. Total program cost, £300. Lives saved, impossible to calculate. But post-war analysis suggests at least 244 pilots owe their survival directly to the restrictor. Hurricane squadrons request the modification. Shilling adapts the design for the Hurricane's Merlin XX engine, requiring a slightly larger orifice of 7.8 millimeters. By June 1941, the entire Fighter Command inventory features either restrictors or improved carburetors based on Shilling's principle. Statistical analysis by the RAF's Operational Research Section shows dramatic improvement. Between August and September 1940, before restrictor deployment, Spitfire losses from engine failure during combat averaged 12%. October to December 1940, with progressive restrictor installation, 3%. January to March 1941, full deployment, 0.8%. The combat exchange ratio shifts decisively. August 1940, 1 British fighter lost for every 1.3 German aircraft destroyed. December 1940, 1 British fighter lost for every 2.1 German aircraft destroyed. The restrictor alone doesn't account for all improvement, but pilots unanimously credit it as crucial. Total confirmed victories by restrictor-equipped Spitfires from September 1940 to May 1941, 832 enemy aircraft destroyed, 413 probably destroyed, 741 damaged. These statistics only count engagements where pilots specifically reported using -G maneuvers enabled by the modification. The Luftwaffe is forced to shift strategy. Daylight bombing becomes unsustainable. They transition to night operations, where fighter interception is less effective. This strategic shift, forced partly by the Spitfire's new capability, gives British cities respite and war production time to expand. Air Chief Marshal Hugh Dowding later states, "The restrictor gave us parity in the vertical plane. Without it, I doubt we could have maintained air superiority through the winter of 1941. It was, quite literally, a war-winning modification that cost less than a pilot's breakfast." Winston Churchill never mentions the restrictor specifically in public speeches, but his private minutes reference it. On December 12, 1940, he writes to Lord Beaverbrook, "I am informed that Miss Shilling's ingenious device has restored our fighters to full capability. Ensure she receives appropriate recognition." Adolf Galland, promoted to General der Jagdflieger, admits post-war, "The British restrictor was a masterpiece of practical engineering. We had superior technology, but they had superior problem-solving. A brass disc defeated our fuel injection advantage. It taught us never to underestimate simple solutions. Economic impact is staggering. Preventing loss of 240 Spitfires saves approximately £2.8 million in replacement costs. More importantly, experienced pilots who would have died from engine failures continue flying. The institutional knowledge preserved is invaluable. Veterans of 1940 become squadron leaders of 1942, wing commanders of 1944. The restrictor influences British industrial philosophy. The Shilling principle enters engineering vocabulary. The simplest solution that works is the best solution. Over-engineering wastes resources. This philosophy influences British design throughout the war, from the Sten gun to Bailey bridges. German analysis of the restrictor leads to their own simplified designs. The FW-190, entering service in 1941, uses a mechanical fuel injection system simpler than the complex Bosch unit, influenced by the effectiveness of Shilling's basic approach. The restrictor principle influences post-war jet engine development. Early turbojets suffer fuel flow problems during rapid throttle changes. Engineers apply Shilling's concept of flow restriction to prevent compressor stall.
The Rolls-Royce Merlin engine incorporates flow restrictors directly inspired by the 1940 design. Modern military doctrine emphasizes rapid field modification based on the restrictor example. The U.S. Air Force's Big Sapphire program, providing urgent operational capabilities, cites the Shilling restrictor as inspiration. Simple modifications deployed quickly can be more effective than perfect solutions delivered late. The variable orifice concept from the Mark II restrictor influences modern automotive fuel systems. Electronic fuel injection systems use similar principles of variable flow restriction based on operating conditions. The 1940 mechanical solution predicts 1980's electronic implementation. Aerospace engineering curricula study the restrictor as an example of elegant problem-solving. MIT's course on Design Simplicity uses Shilling's solution as a case study. Students learn that innovation doesn't always mean complexity. Sometimes it means seeing obvious solutions others miss. The restrictor enters popular culture as a metaphor for ingenious simplicity. Pulling a shilling becomes RAF slang for solving complex problems with simple solutions. The phrase spreads to British industry, then internationally. Management consultants in the 1960s teach the Shilling method of problem-solving. NATO combat doctrine incorporates lessons from the restrictor deployment. Rapid field modifications based on combat experience become standard procedure. The F-4 Phantom's gun pod addition in Vietnam, the A-10's armor upgrades in Iraq, both follow the precedent of Shilling's rapid response to operational needs. Modern air forces maintain urgent operational requirement programs modeled on the restrictor's development cycle. Identify problem, develop simple solution, test immediately, deploy widely, refine continuously. The 72-hour cycle from problem identification to combat testing becomes the gold standard. The restrictor's influence extends to space programs. When Apollo 13 needs an emergency CO2 scrubber, engineers remember Shilling's approach. Use available materials, simple design, immediate implementation. The square-to-round adapter that saves the crew follows the restrictor philosophy perfectly. Current fifth-generation fighters incorporate the lesson. The F-35 software can be updated rapidly based on combat experience, following Shilling's principle of immediate response to operational needs. Complex aircraft receive simple fixes when simple fixes work. Beatrice Shilling continues at the Royal Aircraft Establishment until retirement in 1969. She rises to Senior Technical Officer, then Principal Scientific Officer. She never becomes Chief Engineer, despite qualifications exceeding many who do. Gender barriers persist even for those who help win wars. She receives the Order of the British Empire in 1948, 8 years after her invention saves fighter command. The citation mentions contributions to aeronautical engineering, without specifying the restrictor. Official recognition remains minimal compared to her contribution. Post-war, Shilling works on rocket-assisted takeoff, automatic transmission design, and supersonic aircraft braking systems. Each project shows her characteristic approach: identify core problem, develop simple solution, test immediately. She holds 12 patents by retirement. She continues racing motorcycles until age 55.
In 1958, she sets a speed record at Silverstone for 500cc motorcycles in her age category. Asked about retirement from racing, she responds, "Why? The reflexes still work and the mathematics haven't changed." Squadron leader James Ginger Lacey, whose near-death experience sparked the restrictor's development, survives the war with 28 confirmed victories. He becomes the second highest-scoring RAF ace. Many victories come from vertical attacks enabled by Shilling's modification. Douglas Bader, the restrictor's first combat tester, is shot down over France in August 1941, with 22 victories. He spends the rest of the war in German prison camps, but survives. Post-war, he campaigns for disabled veterans and dies in 1982, never forgetting to credit Tilley's Gadget for several victories. Jeffrey Quill, who championed the restrictor, becomes managing director of Vickers Supermarine. He ensures Shilling receives consulting contracts post-retirement, providing income her pension doesn't reflect. He calls her the engineer who saved the Spitfire when it mattered most. Tilly Shilling dies on November 18, 1990, aged 81. Her obituary in the Times mentions the restrictor briefly. Aviation publications provide more detail. The Imperial War Museum adds a restrictor to its permanent display with the caption, "This simple device saved countless lives and helped win the Battle of Britain." In 2018, the University of Manchester names its engineering building after her. The dedication reads, "Beatrice Shilling, 1909 to 1990, engineer, innovator, and proof that the best solutions are often the simplest." Students call it Tilley's Place. July 10, 1940, the RAF faced an impossible problem. Their best fighter couldn't perform the combat maneuver pilots needed most. German technical superiority seemed insurmountable. The Spitfire, designed to save Britain, was failing at the worst possible moment. By December 1940, that same Spitfire dominated the skies. Not through complex redesign or massive expenditure, but through a brass disc worth 2 shillings. The solution everyone dismissed as too simple proved more effective than any complex alternative. The numbers tell the story. Before the restrictor, 12% combat loss rate from engine failure. After, less than 1%. Cost of development, £300. Value of aircraft saved, £2,880,000. Lives, hundreds.
War immeasurable. The German invasion of Britain, Operation Sea Lion, was cancelled on September 17, 1940. Hitler cited inability to achieve air superiority. The Luftwaffe couldn't sustain losses against supposedly inferior British fighters. Those fighters were inferior until a motorcycle racing female engineer fixed them with a piece of brass. History pivots on such moments. A woman engineer, dismissed as the Carburetor girl, sees what senior designers miss. A solution so simple it seems insulting proves more effective than complex alternatives. A 2-shilling part changes the course of the war. The restrictor that critics called Miss Shilling's Orifice with derision is now displayed in museums with reverence. The plumber's solution that Rolls-Royce engineers mocked saved the aircraft engine they designed. The modification, too simple to work, helped save Western civilization. As Tilly Shilling said in a 1960 interview, "Engineers often overlook simple solutions because they're trained to solve complex problems. But physics doesn't care about your ego. If a brass disc with a hole solves the problem, then that's good engineering. Anything more is showing off."